virtualization. For instance, firmware does this in one part of its products, and yeah, as we see, it's working. I mean, it's quite fast, but we are far from native speed, and it's really dirty. So we want to do something different. Dynamic recompilation. Like binary rewriting, but a little bit more tricky. So dynamic recompilation is you pass one opcode, you behave again like the processor, but this time you don't rewrite it or do something, because it could be possible and different architecture. You pass it, you know the instruction, you recode the instruction into small C instructions, and while you keep care about the virtualized infrastructure, and then you translate these C instructions again into native machine code. So this is really funny, and because it happens to be quite fast, it's possible to support a different architecture than the host OS. You need only user mode support, so there's no kernel module you must load, and it's simple functions. Probably you know QEMU. Yeah, QEMU is one example for dynamic recompilation. And if you look at the progress of QEMU, you see it's working, and it's quite fast in incorporating new processor architectures. So, and it's a one-person project. So this is a technique used, which is really impressive in its results. Yeah, the bad things on this side is, okay, it's a little bit delicate, at least. I mean, it's not very dirty, okay? And also, again, you need to some way support self-modifying code, but it works. Yeah, sometimes you don't want to make a virtualization, a whole virtualization machine. You just want a API emulation. Everybody should know about Wine, I think. Does everybody know about Wine? Oh, okay. Wine is API emulation of the Windows API running on top of Linux. So basically that means API emulation is you have your Windows binary, and of course you want to run it on top of Linux or on top of FreeBSD. Insert your favorite open source operating system here. And to run this Windows binary, well, of course you need Windows, but you don't have Windows. So you need at least the function calls Windows supports. So, and this is where API emulation begins. You have, of course, beside of the loader and some relocation and other small support stuff, you have, yeah, all function calls usually used in Windows mapped to a library, which then calls x11 Linux operating system calls. So this is quite good, and for those whose who have already tried this. Sometimes, well, it depends on the application, but right now there are many applications working, and many others are don't work. Why? Because I mean it's quite fast, and also it's user space, so you don't need something like a kernel module. But as that the Windows binary is expecting exactly the same trash for what it was built, it expects the same bugs also. So in case you have the source, this is not complicated, but in case you don't, it gets really, really, really hard. So you need to emulate every bug found in the system you want to emulate. In case of Windows, maybe you know that there are plenty of bugs. You need to be compatible with any of them. So also you need to emulate a lot of libraries, and this makes API emulation quite a hassle. You know, but if the program you want to use already works, use it. The bad thing on the other side is, well, it's hard to secure, especially if we are doing OS emulation. I want to, as I've mentioned before, user mode Linux falls in the field of OS emulations. That means you're basically taking the Linux kernel. I mean, user mode Linux is already integrated into the kernel, and wrap around the hardware, and instead of writing to real hardware, you are just writing to a Linux kernel. So you need to remap the hardware access, the functions, and all the OS calls the applications want to call must be remapped to the real OS. This is quite hard to secure, and probably for speed you need a kernel module. But user mode Linux is working, and it has its field of application. But we have other approaches also. Well, this is maybe not wide known as an approach for virtualization. I mean, microkernels are, of course, well known to plenty of you. But VMware used this approach, and I think it's VMware ESX or GSX. Always swap these two. I think it's ESX, I mean enterprise something. And in VMware ESX they did something different. The guys from Xen tried it also, they failed. Well, I mean, it's a good approach to take a microkernel which has a built-in possibility to rewrite operating system calls from one flavor to another. I mean, you need at least for every operating system flavor call, you need a management API. But basically, it's good and it's easy. So you have here it's probably a little bit unclear, but in this case you have at least two translation APIs, one translating from Linux syscalls to the microkernel and one translating from Windows syscalls to the microkernel. Well, it's a very clean implementation, and Uh, it's fast, but why did the open source project fail in this implementation? You need lots of code. Especially you need every device driver. You know, probably if you have looked at the kernel code of Linux, you will see that most of the code lines are drivers of devices. So basically, and hardware is changing fast. So, I mean, at FineWeb somehow they did manage to make it, but there is no open source implementation of this because you need to write a lot of device driver, and after half a year you need to write new ones. So, let's come to power virtualization. Power virtualization, the most prominent example of this is Xen, is making a little bit of different approach. If we can't virtualize the hardware because of some minor bugs into the hardware, okay, we work around these minor bugs not in emulating it, not in binary rewriting it. No, we change the operating system, just in small pieces. So basically we want an ideal hardware where every single access to the hardware is going to a management API in the monitor, in the virtual machine monitor. And we don't want to write drivers, so we are using the host OS to pipe the drivers to guest OS, the data to guest OS, and we just need a thin, very thin layer of virtualization between the real hardware, because we modified the operating system not to call the hardware direct, because we want to call the machine monitor instead. So the good thing, this is, if implemented right, this is very fast. Also, it's capable, scalable. Mean you have a linear overhead, and the hardware support, of course, is easy. You're using your host OS for it. On the bad side, you need a modified kernel, and means you won't. There was in the lab there was a Windows version they modified, and didn't take so long. But in reality, Microsoft or commercial operating systems have no real fun about running on top of open source operating system. So that won't happen, even if it's not complicated. And comparing to the microkernel approach, probably forgot in the last slide, there is also one difference on the bad side. In the microkernel approach, of course, you have your device drivers, you're doing all the stuff by yourself. Here, if the host or one hardware domain crashes, well, every other domain which needs data from this hardware domain is also halted. And this was what's coming up next in the next few months. I mean, it's already running, but you don't get a hardware for it. You can, of course, combine power virtualization with virtualization as soon as the hardware gets better. There are a few differences between the power utilization.